Welcome to the Crazy Hat Chemist. So another video here on equilibrium. So let's get moving. Bam! So today we are talking about the Haber-Bosh process in equilibrium shifts with many different examples in here. But before we discuss this, I want you to take a look at this diagram and setup here. On the far left-hand side, you should see that at the top upper left-hand corner on the left-hand side, you should see N2 and H2, and that says feed gases. So that means that you're adding nitrogen gas and hydrogen gas with a compressor. That means it's increasing the pressure. It's going into the system on the left-hand side where there's a heat exchanger, there's a catalyst. That means you're increasing the temperature with that heat exchanger. Okay, there's a catalyst. This catalyst only works at high temperatures, between 400 and 500 degrees Celsius. Okay, and then there's a heater in there. Okay, so what happens is that the nitrogen and the hydrogen react with the assistance of the catalyst at the high temperature to produce ammonia. That's NH3. Now at the top of that cylinder on the left, you should see that there's NH3, ammonia, and unreacted nitrogen and hydrogen gases coming out and then going through the heat exchanger. Okay, so that heat exchanger continues with all three of those gases, cooling them down, and then on the right hand side you should see that the condenser cools down all three gases, that is the ammonia, the nitrogen, and the hydrogen. And then at the very bottom at the storage container is liquid ammonia. Now this condenser doesn't cool down all three of the gases enough to cool down the hydrogen and the nitrogen down to the liquid state. So you are separating out via a boiling point, if you will, condensation point, such that the ammonia will be in the liquid state and the nitrogen and hydrogen gases will be recycled back into the system. Okay, they're cool now, but they were going to be heated up in the heat exchanger in the middle, and then via a compressor they're shoved back into the system where the catalyst is and the heat exchanger to heat it up and then produce more ammonia. So this is a very efficient system. Okay, historically this is a very significant process for the production of nitrogen for Germany. Okay, and this continues to be a major source of ammonia production today. In fact, we use the same exact system that Haber and Bosch set up and modified. Okay, Fritz Haber, a German chemist, earned the Nobel Prize in Chemistry in 1918, and Carl Bosch, who made some modifications on this process, he was also a German chemist, and he earned the 1931 Nobel Prize in Chemistry. Okay, there's much controversy that surrounds these two scientists. Whether they should have received the Nobel Prize, whether they should not have received the Nobel Prize. There's a lot of controversy surrounding Fritz Haber especially. Okay, so you might want to look that up online and figure out what happened to Fritz Haber and his family and what did he promote as far as the German warfare machine, and then also the same with Carl Bosch, and figure out what happened there. It's a very, very interesting story, and there's positives and negatives on both sides. But ultimately, right here today, what I'm focusing on is the equilibrium shift dealing with this reaction, and knowing that they did such a great job chemically organizing this that we use it still today to produce ammonia, which is fixed nitrogen. And otherwise, only certain plants, legumes, will do this production here of ammonia. That is fixing nitrogen, not producing ammonia, but fixing nitrogen. Okay, so we're going to take a look at a variety of different equilibrium shifts with this equilibrium reaction. So on the reactant side, on the left-hand side, I have nitrogen gas, 1 mole of it, and I have 3 moles of hydrogen gas. Then I got the double-headed arrows and one product. That one product is 2 moles of ammonia gas. And then I have a delta H of equaling negative 92.5 kilojoules. Okay, all right, so what does this mean? What does the delta H mean? The delta H is the enthalpy term. This is a change in enthalpy. It happens to be negative. So we need to figure out from this negative value where this belongs on the reaction. Okay, because it is negative, that means that it is exothermic, that is heat liberating. Okay, and it belongs on the product side. Now, notice when I put this heat term on the product side, I actually put a positive sign in it, or right in front of it. That positive sign is just like when I add another product on the product side, I just add a positive sign in between the formulas of either the reactants or the products, right? There's always a positive sign, there's never a negative sign. Okay, the side of which it belongs, either the product side or the reactant side, lets me know whether it is exothermic and negative, as it is here, or endothermic and positive, like the previous lecture that I gave you. Okay, all right, so what is the Keq for this equation here? So remember, the Keq is the equilibrium constant expression, that is products over reactants with the stoichiometric coefficients as exponents. Solids and liquids are not included in any Keq expression. So this one's pretty easy. There are no solids and liquids. Everything is a gas. So this is the Keq expression right here. And that is ammonia to the second power divided by nitrogen to the first power and hydrogen gas to the third power, right? That's a cubed term. All right. So now we got the Keq expression. So here's the Keq at 25 degrees Celsius. That's 3.5 times 10 to the 8. That's approximately at room temperature. That means that, and then we have the Keq at 450 degrees Celsius. Okay, notice that this value at 450 is 1.6 times 10 to the negative 1. So the Keq at 25 is product favored by quite a lot because that exponent is 8. That is a huge product favored reaction. However, at 450, this reaction is reactant favored because it's to the negative 1. Now, if you remember from the diagram that I had showed you before, the reaction is carried out between 400 and 500 degrees Celsius. It is not carried out at room temperature. And the only reason that this is the case is because the catalyst does not work at room temperature. It does not work at lower temperatures. Okay? And the catalyst works at higher temperatures. So the reason that this reaction is performed at higher temperatures is because the catalyst only does its job at high temperatures, even though the reaction is reactant favored. Okay. All right, so what is the direction of shift if the following cases occur? So I'm going to do these individually. So number one, if I decrease the ammonia. So I'm going to find ammonia in my reaction here. And here's the ammonia. I'm going to decrease it. So which way will it shift, to the right or to the left, towards reactants or products? Okay, it was going to shift towards the right, because if I decrease it and remove it, it will shift to the right, towards products. Now, in the diagram that I showed you at the very beginning, what did Mr. Haber and Bosch do? They decreased the ammonia concentration by removing it, by condensing it from the gaseous state to the liquid state. So they effectively removed it, and that shifted the reaction towards products, and they're trying to make more products. Okay, number two, an increase in pressure. So an increase in pressure means a subsequent decrease in volume. Okay, if there is a decrease in volume, then there's going to be a shift to the side with the fewest number of moles of gas. Remember, you do whatever the volume does, but in terms of moles of gas. If the volume is going down, you go to a decreased number of moles of gas. So I'm going to count the number of moles of gas on the reactant side and the moles of gas on the product side, and I've written that right above the arrow right here. So 1 mole of nitrogen, 3 moles of hydrogen, that's a total of 4 moles on the reactant side, and a total of 2 moles for the ammonia on the product side. So which side has the fewest number of moles? The product side. So when I increase the pressure, I decrease the volume, and I shift towards the side with the to the right with the products. Again, this is why Haber and Bosch increase the pressure. So as you are adding more and more nitrogen and hydrogen gas to the system initially at the very top left-hand corner, and then recirculating it back into the system, again, both of them under pressure, okay, then that increases the pressure. You're not actually decreasing the volume, but this is the shift that occurs, and this is how you acquire that, okay? All right, now the next one is number 3, which is an increase in heat. So we already discovered that the change in enthalpy is negative at negative 92.5. That means that it's exothermic. That means that the heat term is on the product side. So if I increase the heat right here, I got my arrow above the 92.5. Which direction will it shift? It will shift to the left. Okay, now, so this is shifting it to the left towards reactants. Now, this might seem counterintuitive. However, this is very important. Okay, so this reaction at this temperature between 400 and 500 degrees Celsius only works at high temperatures with the catalyst. And that is why there's an increase in temperature. That's why Haber and Bosch increased the temperature. Not to make the reaction go to products, but they had to do it because of the catalyst. All right. The next one is the addition of nitrogen. So if I add nitrogen, which way will it shift? To the right or to the left? So I'm going to shift it to the right. So I'm going to shift this towards products. Again, this is making more products as I add more nitrogen to the system, either initially or by recycling it back in there. You're doing these both simultaneously. The next one is the addition of hydrogen gas. So if I add hydrogen gas, it's on the reactant side, it will cause a shift to the right. That will cause it to shift towards the products. Again, they're adding more hydrogen gas, and that's causing a shift towards products, exactly what you want, because you're trying to make more ammonia. Number 6, the addition of a catalyst. Now, you don't see the catalyst here in the equation, but you will hopefully understand that the catalyst lowers the activation energy barrier, but it doesn't cause a shift in the reaction. So this makes both the forward and the reverse reaction rates occur faster. That means the whole reaction occurs faster, but there's no actual change or shift in the reaction due to the equilibrium of the catalyst. Hopefully that worked out. Okay, we got some more examples here. So here we go. The same equation. I won't have to do that again. Now the Kc for this one, because is 375, is going to be 1.2. Okay. Given the associated Kc value, is the reaction reactant or product favored? So 1.2, is that greater than 1, less than 1? Well, of course, it is. The Kc here is greater than 1. And if it's greater than 1, then it is product favored. Okay? Given the following information, determine if the reaction is at equilibrium at 375 degrees Celsius. So the concentration of nitrogen here, I'm just giving some random values, is 0.34 molar. The hydrogen is at 0.76 molar, and the ammonia is at 0.23 molar. So remember the Keq expression? Okay, that is products over reactants with the stoichiometric coefficients as exponents. We're using that same equation here, but now it's called the Q. And the reason it's called the Q is because we don't know if the system is at equilibrium or not. So this is called the reaction quotient, otherwise known as Q. Okay, so if the Q and the K are equal to each other, we know we're at equilibrium. When they are not equal to each other, we know we are not at equilibrium. We know that the K is 1.2. So let's plug in the values that were given here for the molarities of the nitrogen, hydrogen, and ammonia. Plug that in there, and let's figure out if this value of the Q is equal to the K. So I'm plugging these values into the reaction quotient expression here, and that gives me a value, a numeric value of 0.35. Okay, so does 0.35 equal 1.2? The answer is no. Okay, so since the Q does not equal the K, the system is not at equilibrium. That is, 0.35, the Q, does not equal 1.2, the Kc, which is at equilibrium. Which way will the system shift in order to approach equilibrium? Remember, this is a dynamic system here. All equilibriums are dynamic. That means that it will shift to the right or to the left. Now, what I want to do is I want to make the Q go towards the K. Now, if you look at the Q expression, you should see that the product is on the numerator side and the denominator are the reactants. So that means that the Q needs to approach the K, and therefore the system will shift towards the right, towards products. That means that I want to make the 0.35 larger That means since the 0.35, I want to make it larger towards the 1.2, and then therefore the products need to increase and it will shift to the right. Hopefully that works. Okay, here's another example. The Kc here is at 720 degrees. I got 2.4 times 10 to the negative 3. Given this associated Kc value, is the reaction reactant or product favored? Okay, this is it is less than 1, therefore it is reactant favored. Okay, given the following information, determine if the reaction is at equilibrium at 720 degrees Celsius. So I got some same concentrations that I used before, that is 0.34 molar for the hydrogen, 0.34 for the nitrogen, 0.76 for the hydrogen, and 0.23 for the ammonia. We're going to plug these values into the Q. Again, the Q is the reaction quotient because I don't know if the system is at equilibrium or not. I'm going to plug these numbers in. This is what I get for plugging those numbers into the reaction quotient. I'm going to get a value. Of course, it's the same value that we got before. So, since Q does not equal the K, the system is not at equilibrium. And that is the 0.35 does not equal the 2.4 times 10 to the negative 3. That is the K. Okay, which way will the system shift in order to reach equilibrium? So I want the 0.35 to go towards the numeric value of 2.4. So the 0.35 is too big, so I need to decrease that value. So since I want to decrease that value, I want to decrease the products, and that is increase the reactants, and therefore it will shift towards the reactants to make that number smaller. All right, got another one here for you. Same equation. I got a Kp now. This is a K for the pressure. We already talked about the difference between Kc and Kp already. This is at 375. I got 4.31 times 10 to the negative 4. Given the associated Kp value, is the reaction reactant or product favored? You're looking at that exponent. Okay, since this Kp is less than 1, it is reactant favored. Okay, given the following information, determine if the reaction is at equilibrium at 375 degrees Celsius. And this time I'm giving pressure values in terms of atmospheres. For the nitrogen, I got 0.862 atmospheres, hydrogen 0.373 atmospheres, and the ammonia at 0.539 atmospheres. Okay, here is my Q. Now, again, this is the reaction quotient. I do not have the brackets this time because I'm dealing with pressure units. Okay, but the same stoichiometric coefficients are there, and it is products over reactants with the stoichiometric coefficients as exponents, so the same K is occurring here. It's just that they are pressure because it's atmosphere. I'm going to plug in those pressure units right in here with the associated exponents as is required, and this is the number that I get. I get 6.49. So, does 6.49 equal, which is the Q, does that equal the K? Most certainly not. So therefore, since they do not equal, that is the Q does not equal the K, we are not at equilibrium. 6.49 does not equal 4.31 times 10 to the negative 4. Okay, so which way will the system shift in order to reach equilibrium? I need to make the 6.49 decrease in value. That means I need the numerator term, that is the product, to decrease, and I need the reactants to increase. So that will cause a shift towards reactants because I want the reactants to increase, the product to decrease, and that will cause the shift to make the 6.49 approach and get smaller towards the Kp value of 4.31 times 10 to the negative 4. Okay? All right, I am the Crazy Hat Chemist, and I got a fantastic crazy hat here for you. Okay? Remember, the Haber-Bosh process is very, very useful. Lots of historicals associated with that, and it's a great reaction to study. Your test or your chemistry professor or teacher will always talk about the Bosch-Haber process. It is the example of an equilibrium reaction. Definitely. Give me a thumbs up if you like that video. Subscribe to my YouTube channel and find me on the web and find my website. It's packed full of information. I'll see you next time for more cool chemistry problems and more crazy hats. Bye for now.